them would be considered soluble by your solubility rules. See what I'm saying? To talk about which is more soluble than another, we need to sharpen our pencil. We need to, go much further than the solubility rules go. But if I gave you a list of 4 ions, 4 positive ions, and I said, which of these are apparently strong Lewis acids and which ones are weak? Ready? Here's a list of 4 positive ions, all of which fit the definition of Lewis acids. Some are stronger than others. How is it that you're going to know which ones are apparently pretty good at attracting electron pairs and which ones are not? How soluble are these with hydroxide ions? How soluble? Not very. Strong Lewis acid? Yep. How soluble?
How do you figure this out?
Solubility rule for the hydroxides, right? So, look at the solubility rule for hydroxide. Is Fe plus 3 soluble with hydroxide ions? No. It's not. How about Mg plus 2? No. Good. How about K plus?
Yes.
Yes. What about Cr plus 3?
No. Yeah.
Well, it's not listed on there, but what's the solubility rule for hydroxides? All hydroxides are insoluble, except, is this one of the exceptions? No. Then your rule says that it's insoluble. Strong Lewis acid, strong Lewis acid, strong Lewis acid. So if I add these to water, they're going to grab a hold of hydroxides, right? Because they have an affinity, an attraction for them. If they attract hydroxides, what happens to the hydroxide concentration? Yeah, because the hydroxides are being taken away by these positive ions from solution. If hydroxide goes down, hydronium goes up, and the pH becomes acidic, doesn't it? Yeah?
Is that soluble in what? Is that soluble in what?
With hydroxide, huh? We're talking about solubility in water, of course.
So if it's insoluble in hydroxide, that means that it's going to form the precipitating.
Well, not necessarily, but if it's insoluble with hydroxide, then what does that tell us about the attraction of those positive ions for hydroxides? It's strong. And if it's strong, when I put them in water, what's going to happen to the hydroxide concentration? They're going to start sticking to these positive ions, aren't they? Right? But what about this one? Are they going to start sticking to that positive ion? No. Because these ions, potassium ions, don't apparently, according to our solubility rules, have a very strong attraction for hydroxide ions. So the attraction for hydroxide ions is our measure of how strong they are as Lewis acids, right? And it illustrates the reason why we talk about attraction for electron pairs in terms of acids and bases. Because when I add ferric ions to water, the water becomes more acidic. Stick a piece of blue litmus paper in there, it'll turn red. Ferric ions, that's not an acid. Yes, it is. It's a Lewis acid, isn't it? Okay? And I mentioned earlier when I introduced Lewis acid-base theory that precipitation reactions are Lewis acid-base reactions. When a positive ion and a negative ion come together to form a precipitate, the positive ion is attracting the electron pairs that the negative ion has. We thought in terms of attractions between positives and negatives, but if we just say precipitates form when positives and negatives attract one another, then why doesn't a precipitate form when I put sodium ions and chloride ions together? It has to do with the strength of a Lewis acid and the strength of a Lewis base as to whether they form an insoluble precipitate or not. Precipitation reactions are Lewis acid-base reactions. How are we doing? This is a lot, I know. Okay? It'd be nice if we had more time. Spend a little more time talking about this stuff and all, but we don't. Okay. Now, one more thing. If I add sodium carbonate to water, the water becomes more basic. Yes? pH goes up. But we don't really have the tools to be able to determine what the pH would be. That's because not all the carbonate ions are going to take hydrogen ions away from hydroniums. So we're not going to be able to figure out what the concentrations of these two things are. But if I add sodium hydroxide to water, I will be able to do that. So if I add enough sodium hydroxide to water to make a 0.01 molar solution of sodium hydroxide, yeah? What is the concentration of hydroxide ion? 0.01. Doesn't each mole of these produce a mole of hydroxide ions? So the concentration of hydroxide ion would be 0.01 molar. If this is 0.01, it's 1 times 10 to the negative 2, then the hydronium would be 1 times 10 to the negative 12, and the pH would be 12. So, in this chapter, we're going to be able to determine the pH of a hydroxide ion solution, whether it's made by sodium hydroxide or lithium hydroxide or magnesium hydroxide. When those things dissolve in water, they're going to produce a known amount of hydroxide ion. So if I have a 0.024 molar solution of potassium hydroxide, the concentration of hydroxide ion is going to be 0.024 molar. Divide that into 1 times 10 to the negative 14. I can find hydronium concentration. Take the log, change the sign. I have the pH. Yes? Okay, one more thing before we run out of time. Coming back. If we know the hydroxide concentration, we know the hydronium concentration. Yes? And if we know the hydronium concentration, we take the log and change the sign, and we have the pH. Yes? All right. Now, what about adding an acid? If I add this acid to water, I make hydronium ions. If I make a 0.01 molar solution of acetic acid, does that mean the hydronium concentration is 0.01 molar? It's not. Because this is a weak acid, very few of these end up forming hydronium ions. So we're not going to be able to calculate the pH of a 0.01 molar solution of acetic acid yet. However, if I add HCl to water, or any one of those acids at the very top, this is such a strong acid that virtually every one of these molecules gives up its hydrogen ion to water. So if I make a 0.01 molar solution of HCl, you with me? Really, I end up with 0.01 moles per liter of hydronium ions. As every one of these reacts. Almost every one. And if the hydronium concentration is 0.01 molar, then at negative 2, the hydroxide would be 10 to the negative 12. The pH would be 2. Log would be negative 2, change the sign for 2. So, we're going to be able to calculate the pH of solutions that are made from a hydroxide-containing compound, like sodium hydroxide, potassium hydroxide. We're going to be able to calculate the pH of solutions of our very strongest acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid. Those ones at the very top, chloric acid. You're going to finish the worksheet. Okay?